Alright, the last section in this chapter is addition of obliquely crossed cylinders. I just realized I skipped one of the practice problems in here, so I'm just going to go through that first real quick. And that one was like way over here. What was it? I guess like the first one. So right here. This is a practice problem that gets you to think about how to calculate cylinder. And remember that cylinder power is the difference in the two meridians, the two primary meridians. Yeah, so that's cylinder power. So this looks like a long problem. It's a pretty interesting, challenging problem. It gets you to really think about the actual structure of the eye and stuff and applying it. So this looks like almost like an extra credit question on the midterm. I remember from last. I mean, not this, but the extra credit problems are really long and detailed. So check it out. The anterior cornea of the eye is a single refracting surface separating air, right, from the corneal stroma. So n prime equals 1.376. If the corneal radius of curvature of this eye is approximately 7.5 millimeters, which is really let's see, it's lagging 0.00. This is 0.0075 meters along the axis, and the radii along the two corneal principal meridians differ by 1%. I think that's tricky. The trickiest part of this problem is understanding that if they differ by 1%, then you can kind of say, well, if R1 is this, you can say R2. This is how I like to look at it. I mean, I wish I could think of a better explanation, but because there are, but I'll just talk about mine. When I see a 1% difference, I think, well, I'm going to multiply it by 1.01 because the 1 accounts for itself. Oh, man. The 1 right here accounts for itself. The 0.01 tells you about the difference, the 1% difference in radius. So then what do I get? That's 0.007575 meters, right? So you have this almost, the radius of this one is really close. This is supposed to be kind of a 3D structure of the cornea. Hold on, maybe like this. Right, the radius of this one is really close, but not the same as the radius of the other meridian, right? We're talking about meridians here, so but it's all just one surface. This is one kind of sphere. Well, I mean, not sphere, but spherocylindrical, spherocylinder kind of thing. So you want to figure out the power in each meridian. Okay. And this is not like a front surface, back surface thing. Oh, okay, my mouse, the pen isn't working again. It'll show up late. Let's see, can I make my computer faster? No. Just type slow. Oops. Okay, so this is how you want to set it up. Because again, we're looking for, in some ways you can say dv and dh. Maybe I'll write that instead of d1 and d2, because d1 and d2 kind of, we use it sometimes as back and front surface. This is dv and dh. Okay, and so you want to use 1.376 minus 1 over r. on both powers. So this r is going to be 0.75. This is 1.376 minus 1 over 0.0075. So you're going to get a certain power, right? Whatever power this is, it's going to be 50.13-ish, right? And the power over here is going to be sorry, my mouse is really laggy again. Like that. Right, we have these two different distinct powers, but they're very similar though. And so the cylinder is simply the difference between the two. Right? D2 minus D1. Yeah. Or, sorry, dV minus dH. Okay, so that's going to be 0.49 diopters. Cool. There you go. That was the first problem. If there are any, there you go. That's the first problem. If there's any questions, just let me know. Moving on to this last section. This is definitely one of the trickiest kind of. It's random. I haven't used it since I learned it last year, but it's about adding cylinder or Spherocyl cylinder torque, surface torque lengths when you can't, when the principal meridians aren't the same. For example, if I gave you, I don't know, plano plus 2 axis 180 and a plano minus 1 at axis even 90, right? Sure. You can add these and subtract these because you can kind of draw the cross and figure it out. Draw the crosses and add them, and then it'd be cool, right? So this is not easy, but more simple addition. Simple, but can't really do that with this. So let's take a look at, we gotta learn by example here. I'm gonna go ahead and erase this. So what happens if we have, when the principal meridians are not aligned, the powers in these are not additive? Alright, so we're gonna first, before getting into it, just to understand you're using this new plotting system. That's not what we're used to, where it's like 0, 90, 180, 275. It's kind of cut in half. Because we only, the whole point of this is to kind of add these polar coordinates of the cylinder. And the cylinder only goes up to 180, so this is just like kind of a shortcut in a way to add cylinders. So this is a really step-by-step thing. You memorize the steps, then you're golden, I think. So let's take, for example, you have this. You have a plano plus 2 at axis 180, and then you have a plano minus 1 so at axis 30. Clearly these are not lined up anymore, so we have to do this method. So first step is to find the spherical equivalent. And the spherical equivalent is basically the sphere, the sum of the spherical. Oh, the spherical equivalent. If you recall, it's up here. Cell over 2. Right. So I'll call this number 1. This is prescription number 2. So ds number 1 is equal to Plano plus 2 over 1 equals plus 1. Alright. And then you get the same thing. You get minus 0.5. So hopefully that's the DS1 is your spherical equivalent of the first prescription. So we're going to keep these numbers, or no, we take these two, okay, and add. That is the next step. Right? It says, well, the spherical equivalent is a sum of these spherical equivalents. I know we're saying spherical equivalent a lot, but it's the sum of these two, and so you get plus 0.50. So we're going to be using that later. Step number 2, convert all cylinders to plus cylinder form if they are not. So this was step 1, right? Step 2, just convert. Prescription 1 is fine. Prescription 2 is going to be, minus 1. Because remember, you add the two together, minus 1. Then you change the sign, plus 1. And then you change the axis, so 90 plus 30 is 120. Alright, now what? That's step 2. Use a double angle coordinate system. So, kind of this thing right here. Let's see. (180). So you might recall plotting vectors in either physics or math. So this is kind of like that, where you have these values of 1 and 2 and 3. Right? I'm trying to make this even here. And you want to plot what? Plot both vectors in a vector form, head to tail, with the magnitudes, the length equal to the cylinder. So we only care about the cylinder right now. So the first cylinder was a plus 2, right? Plus 2 at 180, so that's kind of the first vector. So I'm going to use a different color. Okay, so then this is the value of 2. See, because 2 hash marks, right? And then so that's number 1, right? And then I'll plot number 2 was also a plus 1. Plus 1. This is why you want to use this, right? A plus 1 at 120. So that's kind of like, if we wanted to estimate 90s, 100, 110, 120. Not over here. So, and then you're really estimating here. So this is 120. I mean, at 1 unit at x is 120. Hopefully you can see that. This is one, I'm trying to just estimate 1 unit, not 2. 2 is like this long, so I'm going to make half of that. And so this is kind of the weird part because, well, you're supposed to do it from head to tail, so technically I'm supposed to do it like here. So I apologize. I mean, it's okay to maybe just do that so that you can kind of see. No, it's good to do this so that you can really see that you're going in this direction. This is about 120 axis. So it's a good thing to start at the origin. Alright, so it's good to start at the origin, because if you don't, you might start here and your line would be more skewed than, because you're trying to go from a farther point to 120, when in reality the arrow should be pointing to 120 from the origin, because that's just how vectors kind of work, I guess. So use this as a tool to point to 120 and then recreate it over here, because we want to have a head to tail kind of thing. Head to tail meaning you go from, when you're done with the first vector, you continue that. So we added the cylinder powers to this cross. The resultant is drawn from the origin to the head of the second vector. So I'm going to draw that in yellow. Okay. Looks kind of like that. The origin to the end, where the end of the blue, right? So the resultant sphere power, this gives the final cylinder power and axis, so you can, it's all about estimation. So the final cylinder looks at about 160, right? Because it's pointing over here-ish. Yeah, 160-ish, and because we had a 2-unit vector going to the right and then kind of 1 going a little bit to the bottom and to the left, we estimate this to be about 1.25 sil, right, at 160. So that's an estimation, 125 at 160. So what are you going to do with that? You're going to use, you want to find the spherical equivalent. We're almost done, right? We're almost done. So step 6, the resultant sphere power can be computed from the fact that the spherical equivalents of the individual lengths add to give SE of the resultant. So you have SER already. SER. Oops. Let me use a black. SER equals S plus sil over 2. And we want to find this. We don't have this one. So you're going to say, in this example, the spherical equivalent was this, remember? So why did we do this in the first place? This is your SER. So you're going to say 0.5. Oh man, I'm starting to really hate this pen. 0.5 equals S plus 1.25 over 2. Again, this sil comes from this calculated this from step number 5. Okay, so then doing some magic here, just getting some math, you get S equals that's your sphere. This is already your sil, and you have your axis already. So the final component out of all of this, the final I just had to write really slow. so that it doesn't lag. There you go. It's lagging so much. Alright, so through that step-by-step process, you're able to go from these two prescriptions that differ, and then you turn it into this one combined estimate of a combination. Yeah, so just to recap, step one is to find the equivalent sphere for both prescriptions. That's right here. You do that, and then you add the two, and you're going to use that number later. Step number two, you change any cells to plus. If they're both plus, then that's good. You don't really have to do anything. Then you graph it using the magnitude of the cell to graph, and then the direction is where you want to go. So over here is 180, right? 180. So you're going to go in the 180 direction first. And then when you get a resultant, that resultant is kind of your money right there that you're going to use later. But before you do that, you have to find the sphere, resultant sphere, using this equation. And the resultant sphere is that S right there. Yeah, and then that's it. So hope that helps. Let me know if you guys have any questions or anything like that. Peace.